So in this video, we're going to go over the Monty Hall problem. Now, the Monty Hall problem is one where you have a host of a game show called Monty Hall, and you have a contestant, let's call him Bob, and behind one of these doors, and the contestant doesn't know, but the host does, is a car, but we have no idea which one. From our perspective, as the contestant, as Bob, we don't know which one has the car. Now, the way that the game works is that the contestant Bob picks a door, and in this case, let's say he's picked this one. And so Monty Hall here is gonna walk over here, and he's gonna open one of these two doors and show you that there's nothing here. And so now you're left with a choice. And Monty Hall is gonna say, well, if you think you chose it correctly, you can stay with your original choice, but I'm giving you the option to switch. And so we want to know what's the likelihood, or what's our chance of winning if we switch versus our chance of winning if we stick with our original answer. And so what I'm going to do is just set up some probabilities. And so I'm going to define the event that W is that he wins the car, and C is the correct door being initially chosen. And so what we're going to do is assume a strategy, S, which is going to be to always switch. So what's our probability under the strategy S of winning? So that's going to be, we can use the fact that we can form a partition of our sample space using C by using C and its complement in S, or in our sample space S, which is not the same S as our strategy, and I've already probably confused some people, so forget about that. But just, we're going to partition our, we're going to use the fact that C and C complement form a partition. And as a result, we can split up the probabilities and use conditional probabilities, as was demonstrated in a previous video about partitions. So the probability of winning, given our strategy S, given C being that he chose the initial door correctly, times the probability C plus, so the probability of winning is the probability of winning given C times probability of C plus the probability of winning under the strategy of given C complement times the probability of C complement. And that's essentially because, he can either guess it correctly or not. And that, however it is we set up our whole formal sample space, it's true that you can either get it correctly or you cannot get it correctly, and that will kind of split your sample space, in such a way where you have two disjoint sets whose union is the entire sample space. So again, in a previous video, when I talked about partitioning sets, I said it was kind of useful because sometimes some of these conditional probabilities are easier to tackle than the than the probabilities, like without introducing this conditional framework. So in this case, we know that the probability of choosing the initial door correctly is going to be 1/3, because it's got 1/3 chance of guessing which one has the car, because it's equally likely to be in any one of them, or is equally likely to guess because he doesn't have ESP or anything like that. So and then here the probability of not choosing it correctly, well, that's going to be 2/3. Okay, so can we tackle these conditional probabilities? What is the probability of winning given that he's chosen it correctly and that our strategy is going to be to always switch? Because that's what we're interested in. essentially, what is the probability of winning under the strategy of always switching? Now, if he guessed it right on the first try, that means the car is going to be here, and these two will not have anything in them. And so what's going to happen is that Monty Hall is going to walk over and he's going to expose one of the two, and then we'll still have one of them being closed. We don't know if the car's there, or it could be the other way, or it could be like that. Okay, so that's essentially going to be the case. Now, if we chose the car correctly in the first guess and we switched, we're definitely going to lose, because we're going to be moving from the correct guess to an incorrect guess, because the car is in this one, it's definitely not here and definitely not here. The car is only behind one of the two, which tells us that this is actually 0. Now, what's our probability now, given that you chose incorrectly on the first choice? Well, in this case, the car could either be here or the car could either be here. And what's going to happen is Monty Hall's going to walk over, and he's not an idiot, so he's not going to open up the door with the car in it. He's going to open up the door that doesn't have the car in it, leaving only the door with the car left. Now, if our strategy is to switch, we will switch to the door with the car. Therefore, under our strategy, the probability of winning, given we've chosen incorrectly, is going to be 1. Okay, and we can say that that's equal to 0 times a third, which is 0, plus 1 times 2/3, which is 2/3. And so that's sort of one way of thinking about or working out the probability of winning under the strategy of switching doors. Another way to think about it is to think that by always switching, essentially you're choosing the other 2 doors. Okay, and so you're winning you know, if you were given the choice, you can either choose 1 door or 2 doors. Okay, you'll always choose 2 doors, or else, you'd be kind of an idiot, wouldn't you? So in the strategy where you're switching, you're essentially choosing the other 2 doors, and so the only way of losing is if your initial guess was correct, and that happens 1/3 of the time. And therefore, as demonstrated, if your strategy is to switch, you will win with likelihood 2/3. Hopefully this was clear. And I'll be posting another video that has another way of approaching this problem, but that uses something called Bayes' theorem. So